So just about every handheld power tool, such as this circular saw or this drill, have got a DC or universal motor in them. And in this video, I'll explain how they work. So here's my Ryobi hand drill, and on the front we got the chuck and some gears. And these are driven by the rotor, which fits inside the stator. So the rotor has got a fan on one side for cooling, and then on here we've got layers of laminated iron with copper windings in between, which are connected to the individual pieces of copper on the commutator. On both ends of the shaft we have a ball bearing, and I'm just going to put this in this block of wood here, and I'll hold that with a clamp. The windings in here and the iron core essentially form an electromagnet, and they're wired up to the commutator in such a way that if I apply electricity from here to here, the north and south poles here will be here and here. So let me demonstrate by applying a little bit of current, like so. And now I'll hold a compass on here, and you can see there's one pole here, and the other side has got the south pole pointing at it. And now the cool thing is, if I move these around somewhere else, the north pole here is always going to be pointing to whichever side I'm applying that wire to. The thing with magnets is that north and south are always attracted to each other. So this magnet is trying to orient itself with the south pole facing north, because north is this way here. So now if I bring the south pole of another magnet nearby, that wants to reorient itself. And so if I bring it in from the side, whichever direction, it's always the north and south that are attracted to each other. So if I have the magnet like this, and I bring this magnet in like so, it wants to rotate this way. This rotor forms an electromagnet, and if I apply just a little bit of current, in this case from a AA battery that I put some leads on with a rubber band, and I apply current here, we've got the north and south poles here and here. And now if I bring a magnet in from the side, it always tries to orient itself towards that. And you notice now it's spinning. So the cool trick is, the north and south poles will always be this way, and with a magnet here it tries to orient itself this way, but as soon as it reorients itself, we're connecting to different contacts on the commutator, so north and south will still be this way, and so the rotation just is continuous. But as a motor, this is actually very ineffective, because magnetic flux travels about 1,000 times better through magnets and through an iron core in here than it does through the air. And if I hold this near, I'm not really getting that much magnetic flux through here, and if I get too near, it just gets stuck. To give the flux a better path, I devised this thing here where I've got this bent piece of iron, and I've got two rare earth magnets here and here. And now if I put the rotor in between, I can have a much smaller air gap, although it's still pretty large for a motor. And the flux can then go around here, so I'll get much more flux going through everything. So let's apply the AA battery again. This time I have to go top and bottom because my magnetic poles are on the sides. And see, you can see it spins, but not terribly fast. Part of this is this rotor is actually made for a 110 volt motor, and I'm only applying 1.5 volts here. Partially what's limiting the speed of rotation here is that as this spins, it generates a reverse voltage just from the changing magnetic field going through the coils. So with this homemade voltmeter set to 1 volt full scale, if I now put the contacts here and I spin this, you can see I get a voltage here, and I can easily get up to about 0.6 volts. And that 0.6 volts works against the battery's own voltage, so cuts down on how much current I can get through. So now back to the power supply and 3 volts on my wires. Let's see how that does. So that already spins a lot faster, but let's turn this up, and now we're at about 30 volts on here, and let's try that again. Now that seems pretty fast, but in an actual drill, this rotor would be spinning 100 to 200 times per second. How powerful a motor this actually is a function of how strong this magnet is and how strong the magnets on the outside are. And this is just a very crude setup. In an actual drill, the magnet around it is very close and much stronger. And with the flux being able to go through iron about 1,000 times more easily than through air, there's a very small gap around the rotor so that we have a lot of flux going through here. Now what I was explaining is how this works as a DC motor, but this is actually a universal motor and it runs on AC. And the way that works is the stator, rather than having permanent magnets in it, actually has electromagnets as well. So with the AC reversing direction 60 times per second, if we had permanent magnets, it would just want to wiggle back and forth 60 times per second, but that's no good at all. But because the field magnets here also reverse in the same way, whenever the magnetism in here reverses, it reverses in here as well. So it's always in the same relative phase with each other, and so it continues to drive in the same direction. Now in a drill, we don't just use a couple of pieces of copper wire to connect to the commutator here. We actually use something called brushes. And we call these brushes even though they're actually just little pieces of graphite, and they go into holders here and here. Now these carbon brushes will slide much better and wear much slower than a copper wire would, but even these brushes wear out. So the brushes are always inside of a spring-backed holder like this thing here, so as the brush wears out it can continue to move forward. But of course eventually there'd be no brush left, and then the motor needs to be serviced, the brush is replaced. And that's why we never use a motor like that in applications that have to run for a very long time, such as a fridge or an air conditioner or a furnace. For things that need to run quietly and reliably for a long time, we use induction motors. This is just a simple shaded pole motor, much like the one that would be used to power the fan inside the freezer of a fridge. And if you look here, there is a stator with a coil on it, but there's absolutely no electrical connections to the rotor, so no brushes to make a lot of noise and get worn out. Induction motors vary from the very small to much larger. For example, this 2 horsepower motor for powering larger tools. In many ways, induction motors are actually simpler than universal motors, but the theory behind them is much harder to explain, so I'll cover that in my next video.